Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, let's solve some problems on torsion. So the first problem is, develop the expressions for the twist angle gamma for the case of concentrated torsional moment T applied at midspan where the ends are torsionally simply supported. So you can see the beam where the ends are torsionally restrained, and this is the plan view of the beam. The ends with torsional restraint, but warping is not restrained, and you can see that the gamma of 0 equal to 0, that is twist is prevented at both ends at gamma of 0 equal to 0 and at gamma of L equal to 0, and you can see that concentrated torque is applied at the midspan and the reaction is given at two ends. The first end is T by 2 and the second end is also T by 2. And the practical representation of the boundary conditions in the problem is shown on the right hand side, where you can see that a column is there, a beam is also attached to the column. Basically, this is a beam column junction and it is connected through clip angles. The only thing that is connected here is the web of the beam connected to the flange of the column, and this is by a clip angle. This will prevent twist, but it will allow warping of the cross section because the flanges are unrestrained. So let's come back to the problem 1. So the solution is given as the generic equation for a member subjected to torsion is given as T equal to Gj into d gamma by dz minus EIW into d cube gamma by dz cube. So this is a third order ordinary differential equation ODE, and let's divide this entire equation with minus EIW on both sides. So we have minus T by EIW equal to d cube gamma by dz cube minus Gj divided by EIW into d gamma by dz. The solution for third order ordinary differential equation is given as complementary solution plus particular solution. Let's take d by dz equal to capital D and root of Gj divided by EIW equal to lambda. So now the differential equation becomes minus T by EIW equal to d cube gamma minus lambda square d gamma. The complementary solution is given as the characteristic equation is d cube gamma minus lambda square into d into gamma is equal to 0. Now we can represent it as d cube minus lambda square into d into gamma is equal to 0. Here either d equal to 0 or d square minus lambda square equal to 0. This can be obtained by taking d as common, and the roots of the equation are given as d equal to 0 or plus or minus lambda. So the general solution for roots of the form 0 plus or minus lambda is given as gamma h equal to a into e power lambda z plus b into e power minus lambda z plus c. We know that e power lambda z equal to cos h lambda z plus sin h lambda z, and e power minus lambda z equal to cos h lambda z minus sin h lambda z. So gamma h is equal to a into cos h lambda z plus sin h lambda z plus b into cos h lambda z minus sin h lambda z plus c. Now we can arrange this equation in the form gamma h equal to a minus b into sin h lambda z plus a plus b into cos h lambda z plus c. A minus b is a constant and a plus b is also a constant which can be replaced as x and y. So gamma h equal to capital X sin h lambda z plus capital Y cos h lambda z plus c. Now the particular solution is given as the non-homogeneous part of the ordinary differential equation is minus T divided by E into IW. Here T is a variable along the length, that is, it is a function of length z. Therefore, the particular solution for ordinary differential equation ODE is given as gamma p equal to f of z. The solution for generic equation for torsional moment T is given as gamma equal to gamma h plus gamma sub p. So this is given as x into sin h into lambda z plus y into cos h into lambda z plus c plus f of z. Let f of z be a polynomial where gamma sub p equal to c1 plus c2 into z. Then let us find the value of constant c2. This is given as d cube gamma sub p divided by dz cube minus gj divided by EIW into d gamma sub p divided by dz is equal to minus t divided by EIW. Now if you look at the problem, we can see that in the plan view, a concentrated torque is applied at the center. The reactions are given as T by 2 at both ends, and the both ends are represented as gamma of 0 equal to 0, which is the twist is restrained at z equal to 0. Similarly, gamma of L equal to 0, the twist is also represented at the other end where z equal to L. and the distribution of torque, which is also called as the torque diagram, is given as T by 2, which goes up, and then at the center there is an opposite T that is acting, so it comes down and there is a negative T by 2 and it goes all the way to the right, and then you can see that there is a T by 2 that is at the end and then at z equal to L, and then it finishes the diagram as shown here. So the T here has to be T by 2, so this equation can be represented as d cube gamma sub p divided by dz cube minus gj divided by eiw into d gamma sub p divided by dz is equal to minus t divided by 2 into eiw. So let's now substitute gamma sub p equal to c1 plus c2 into z. So we have d cube by dz cube into c1 plus c2 into z minus gj divided by eiw into d by dz of c1 plus c2 into z is equal to minus t divided by 2 into eiw. So when we do so, we know that the first term will be 0 because d cube by dz cube will be 0 because the first term here is c1, which is a constant, will be 0, and then the second term c2z will be 0 once you differentiate it thrice. So the next term, which is differentiation only once, we have minus gj divided by eiw into c2 is equal to minus t divided by 2 eiw. So c2 is given as t divided by 2 eiw into eiw by gj. On further simplifications, we get c2 equal to t divided by 2 into gj. So then the particular solution gamma sub p equal to c1 plus t by 2 gj into z. So the entire solution becomes gamma equal to x into sin h lambda z plus y into cos h lambda z plus c plus t by 2 gj into z. Here the constants c1 and c is merged as c again, as you can see from the equation. So let us now find out the value of constants x, y and z using the boundary conditions. So the solution for this ODE is given as gamma equal to x into sin h lambda z plus y into cos h lambda z plus c plus t divided by 2 gj into z. So we know that the twisting is arrested, so gamma of 0 equal to 0 and gamma of L equal to 0. At the center there is a concentrated torque that is happening T, and the reaction is given by T by 2 on both sides. So we also know that gamma double dash of 0 equal to 0 and gamma double dash of L equal to 0. Now let us find out how this is happening. So if you look at fixed cantilever, which is fixed on one side and free on the other side, and a torque is applied on the free end, we can see that the resistance offered to the torque is basically an uniform torsion or a torsional shear that is happening at the free end, and this is called Saint-Véran's torsion as well, and this is happening away from the support. Now in between the supports you have lateral shear plus torsional shear is actually providing resistance to the applied torque, and at the fixed support non-uniform torsion happens, which is T1 at the supports where there is warping normal stresses that is taking place as well as lateral shear in the flanges that takes place. So the lateral bending in the flanges here is given as m sub f equal to EIF into d square gamma by dz square, which is not equal to 0 because the warping is arrested at the fixed end. However, this is not the boundary that is being discussed in the problem here. The boundary that is being discussed in the problem is shown in the figure here, as you can see. So you can box it at this location where the twisting is prevented but warping is allowed. So the lateral bending in the flanges m sub f equal to EIF into d square gamma by dz square is equal to 0. EIF cannot be 0 because it is a property of the material. So d square gamma by dz square is equal to 0. So d square gamma by dz square is represented as gamma double dash, which is shown here. So the gamma double dash at both ends of the beam, as you can see here, is 0. So at z equal to 0 and z equal to L, gamma equal to 0. Similarly, the boundary condition 2 is given as at z equal to 0 and z equal to L, d square gamma by dz square is equal to 0. So using the first boundary condition, we get at z equal to 0, gamma equal to x into sin h into lambda of 0 plus y into cos h into lambda of 0 plus c plus t by 2 gj into 0 is equal to 0. Sin h into lambda of 0 equal to 0, and the fourth term t by 2 gj into 0 is also equal to 0. So we have y plus c equal to 0 because cos h 0 is equal to 1. So we have y plus z equal to 0. Now let's differentiate this gamma equation, which is d gamma by dz equal to x into lambda into cos h into lambda z plus y into lambda into sin h into lambda z plus t by 2 gj. Now when we differentiate it one more time, we have d square gamma by dz square equal to x into lambda square into sin h into lambda z plus y into lambda square into cos h into lambda z. And using the second boundary condition, now we get at z equal to 0, gamma double dash is equal to x into lambda square into sin h into lambda of 0 plus y into lambda square into cos h into lambda of 0 is equal to 0, which gives rise to the value x into lambda square into 0 plus y into lambda square into 1 is equal to 0, which indicates that y equal to 0. Now substitute y equal to 0 in the previous equation, we get y plus c equal to 0. So when y equal to 0, c equal to 0. So now substituting y equal to 0 and c equal to 0 in the original equation, we have gamma equal to x into sin h into lambda z plus t divided by 2gj into z. Now let us find out x. So we need another boundary conditions to understand and to find out x. So recall the plan view of the beam. You can see that a concentrated torque is applied at the center, and then T by 2 and T by 2 are the resistance offered to the concentrated torque happening at the center at the edges T by 2 and T by 2 at both ends of the beam. What we are seeing here is the top view, which is what you see here is basically the flanges, the dotted line that represents the web. So here when we draw the torque diagram, we have T by 2 at one end and T by 2 also at the other end. And the distribution of torsional moment T is a combination of Saint-Venant's torsion T sub S plus warping torsion T sub W, which is equal to the total applied torque T by 2 at the ends. So the distribution is given as shown in the figure here. The Saint-Venant's torsion T sub S basically is the red color line, which is a spline or a cubic equation. As you can see, the maximum is happening at the edges or at the boundaries, and minimum is happening at the center. Whereas the non-uniform torsion, which is warping torsion TW, is minimum at the edges and maximum at L by 2. So the distribution of Saint-Venant's torsion T sub S equal to Gj into d gamma by dz is plotted here, which is maximum at the ends and minimum at the midspan. And the next one is basically the green color lines that you can see, which is T sub W, which is the warping torsion or the non-uniform torsion. The distribution is given as Tw equal to minus EIW into d cube gamma by dz cube, which is minimum at the ends and maximum at the midspan. Now at midspan, the torsional moment is governed by warping torsion. However, the torsional moment due to Saint-Venant's torsion is minimum at the midspan. So T sub S equal to Gj into d gamma by dz is equal to 0 at midspan, as you can see from the figure here. So at z equal to L by 2, d gamma by dz equal to gamma dash is equal to 0. So using this condition, we can substitute and find out the value of x. So let us find x using this boundary condition. So at z equal to L by 2, d gamma by dz equal to gamma dash is equal to 0. So gamma is given as x into sin h into lambda z plus t by 2 gj into z. So gamma dash is given as lambda into x into cos h into lambda z plus t by 2 gj. So now substitute z equal to L by 2, we have lambda into x into cos h into lambda L by 2 plus t by 2 gj equal to 0. Now x is given as minus t divided by 2 gj lambda into cos h lambda L by 2. Now substituting the value of x in gamma, we have gamma equal to minus t divided by 2 gj into lambda into sin h lambda z divided by cos h lambda L by 2 plus t by 2 gj into z. Now we can further simplify this by taking t by 2 gj lambda outside common. We have gamma equal to t by 2 gj lambda into lambda z minus sin h into lambda z divided by cos h into lambda L by 2. So this is the solution for the first problem, which is gamma equal to t divided by 2 gj into lambda z minus sin h into lambda z divided by cos h into lambda L by 2. Now let us solve the problem 2. As you can see here, a W500 into 300 into 129.77 kg per meter beam on a 8 meter simply supported span is loaded with a concentrated load of 200 kN at the midspan. The ends of the member are simply supported with respect to torsional restraint, which is gamma equal to 0, and the concentrated load acts with an eccentricity of 50 millimeters from the plane of the web. Compute the bending and torsional stresses. So this problem can be solved based on the derivation that we did in the previous problem. So there is a connection between the problem 1 and then problem 2. Problem 1 was theoretical in nature. Problem 2 will be an application of problem 1. So you can see that this is a beam 8 meters in length and load of 200 kilonewton is applied at the midspan. So there is an eccentricity of 50 millimeters, which leads to a torque, and then at the ends gamma of 0 equal to 0 because there is a torsional restraint, and then at gamma equal to L is equal to gamma of L equal to 0, and at the one end gamma double dash of 0 equal to 0, and the other end gamma double dash of L is equal to 0. So you can see from the picture on the right hand side, P equal to 200 kilonewton acting eccentrically to the web. The eccentricity is measured as 50 mm, and at the plan view you can see here there is a T that is happening at the center, and then T by 2 happening at the ends of the beam. The actual dimensions are given here, which is an I section. The width of the I section is 300 mm, the depth of the I section is 500 mm. The thickness of the flanges are 27 mm top and bottom, and the thickness of the web is given as 11.5 mm. Now recall the same problem that we did in the previous problem. The torque diagram is given as here, and the distribution of torsional moment is a combination of Saint Venant's torsion T sub S plus warping torsion T sub W is equal to T by 2. The distribution is happening in a nonlinear fashion, as you can see here. So the T sub S is the Saint Venant's torsion, which is basically maximum at the ends and minimum at the center. The distribution of Saint Venant's torsion is given as T sub S equal to Gj into d gamma by dz, which is maximum at the ends, minimum at the midspan. And then the other one is the warping torsion given in green color arrow marks, as you can see here. And the distribution of warping torsion is given as Tw equal to minus EAW into d cube gamma by dz cube. And this is minimum at the ends and maximum at the midspan. Now from the previous problem, the solution of torsional moment T of a simply supported beam with ends torsionally restrained gamma equal to 0, but warping unrestrained, which is gamma double dash is equal to 0, is given as gamma equal to T by 2 Gj lambda into lambda z minus sin h into lambda z divided by cos h into lambda L by 2. So let's find out the required parameters here, T, J, IW, lambda and L. The torsional moment here is given as T equal to force into the eccentricity, which is 200 kilonewton acting at the center. The eccentricity is 50 mm, which is given as 0.05 meters. So the torsional moment is given as 10 kilonewton meter. The length of the beam is 8 meters. The other parameters are J, which is the torsional constant, IW, warping constant, and lambda. So calculation of the section properties. So the torsional constant J is first needs to be calculated. Before we calculate that, we need to find out the slenderness of the plate. Depending upon the slenderness of the plate, the equations for J will vary. Here the slenderness of the flange plate is B by T, which is 300 divided by 27, which is 11.11, greater than 10. Similarly, the slenderness for the web is D minus 2T by T, which is equal to 500 minus 2 into 27 divided by 11.5, given as 38.78, which is also greater than 10. So we can use the formula J equal to 1/3 BT cube, and so J is given as 2 into B into T cube by 3 plus D minus 2T into T cube by 3. Here the 2 is given as for the top flange as well as for the bottom flange. So 2 into 300 into 27 cube by 3 plus 500 minus 2 into 27 into 11.5 the whole cube divided by 3. So this value comes out to be 4.16 into 10 power 6 millimeter power 4. The warping constant IW is calculated as IW equal to IF into h square by 2. IF represents the flange bending in the minor axis, and h is the distance between the flanges, which is the center to center between the top flange as well as the bottom flange. So the minor axis bending moment of one of the flanges is given as 27 into 300 cube divided by 12 into 500 minus 27 the whole square by 2. Here 27 basically is the center to center, so you have to subtract 27 by 2 at the top and 27 by 2 at the bottom. So this becomes 500 minus 2 into 27 by 2 divided by 2, that becomes 500 minus 27. So this value is equal to 6.79 into 10 power 12 millimeter power 6. So lambda equal to root of Gj divided by EIW. When we do so, we have Gj divided by E can also be represented as 2G into 1 plus nu into IW. The reason that we represented E in terms of 2G into 1 plus nu is simply to cancel the G at the top and bottom. So we have the value which is 4.16 into 10 power 6, that represents j, divided by 2 into 1 plus 0.3, the 0.3 is the Poisson's ratio, into 6.79 into 10 power 12, which is the I sub w value. So lambda is given as 4.85 into 10 power minus 4. Using these, let us find out the shear and normal stresses. So the pure torsion or Saint-Venant's torsion is given as torsion that is resisted by developing shear stresses in the flanges and web alone. So from the torsion equation, we have T by J equal to tau by R. T is the torsion, J is the torsional constant, tau is the shear stress, and R is the radius from the center. So tau sub S equal to TR divided by J. So when we put R equal to T, we have TT by J. And we know that for non-circular cross section, T equal to Gj into d gamma by dz. So we have T by J equal to G into d gamma by dz. Now we can substitute that in the above equation, which is tau sub S equal to capital T into small t divided by J. So T by J can be represented as G into d gamma by dz multiplied by T. So we have this equation, and then we can substitute d gamma by dz from the equation of gamma equal to T divided by 2Gj into lambda z minus sin h into lambda z divided by cos h into lambda L by 2, which is what we got in the previous problem, which is the equation for gamma. Now we have to use this equation and we have to differentiate it with respect to z. So when we do so, we have Gt into T divided by 2Gj into lambda minus lambda into cos h lambda z divided by cos h lambda L by 2. Right. So when we simplify that further, we have tau sub S equal to T into T by 2J into 1 minus cos h lambda z divided by cos h lambda L by 2. Here the tau sub S is maximum at z equal to 0 and tau sub S equal to 0 at z equal to L by 2, because tau sub S represents the Saint-Venant's torsion or uniform torsion, which is maximum at the ends and minimum at the midspan. So basically you can see here the nonlinear distribution in the red color curve on the right hand side, which is representing the uniform torsion, which is 0 at the midspan. Now for flanges, let's substitute the value of T equal to 27. So when we substitute it, we have 27 into 10 into 10 power 6 divided by 2 into 4.16 into 10 power 6, which represents the J value, into 1 minus of 1 by cos h into 4.85 into 10 power minus 4, which represents lambda, into length, which is 8000 divided by 2. So the value is 23.31 MPa. Now let's do for the web. The value of T for the web is 11.5. The same equation, we substitute the value of 11.5 and do the same routine. We get a value of 9.93 MPa. Now this can be represented graphically, as you can see on the right hand side, which is the shear stresses due to pure torsion or uniform torsion or Saint-Venant's torsion. Now let us find out the lateral bending of the flanges, which is warping torsion. Recall that the torsion resisted by developing shear stresses and normal stresses in the flanges. The shear stresses in the flanges are given as the lateral shear force V sub F equal to minus EAF into H by 2 into d cube gamma by dz cube. We know that the shear stresses due to warping is given as tau W equal to Vf into Qf divided by If into Tf, which is nothing but Vq over It, which we studied in our basic strength of materials course. So the statical moment of area about y-axis, which is Q sub F, is given as A into x bar, which is given as B into T divided by 2, which is the area of one half the flange, and B by 4, which is the lever arm distance. So if you look at the figure on the right hand side, you can see that the highlighted portion is basically the one half of the flange, whose area is B by 2 into the capital T thickness, and B by 4 is one half of B by 2, which becomes the lever arm with respect to the center of the web. So that is given. W now becomes E into I sub F is nothing but T into B cube divided by 12 into H by 2 into d cube gamma by dz cube into Bt divided by 2 into B by 4, which is the value of Q, divided by B cube T divided by 12, which is I sub F, into T, which is the thickness of the flange. Now we have d cube gamma by dz cube equal to d cube divided by dz cube into the gamma is given as T divided by 2 Gj into lambda z minus sin h into lambda z divided by cos h into lambda L by 2. When we differentiate it 3 times, the first term in the equation becomes 0, the second term becomes now minus lambda cube into cos h into lambda z divided by cos h into lambda L by 2. So we can further simplify this by T by 2 Gj into minus lambda square into cos h into lambda z divided by cos h into lambda L by 2. And we know that lambda square equal to Gj divided by EIW. So when we back substitute it and further simplify this, we can remove Gj on both sides. So we have d cube gamma by dz cube equal to T divided by 2 EIW into minus of cos h into lambda z divided by cos h into lambda L by 2. We can substitute this in the entire equation for tau w. So when we do so, we have E into b square h divided by 16 into T divided by 2 EIW into minus of cos h lambda z divided by cos h lambda L by 2. So this is the equation for shear stresses in the flanges. You can see that the shear stresses in the flanges is given as Tw. Basically the Tw is minimum at the edges and maximum at the midspan. So Tw is minimum at z equal to 0 and maximum at z equal to L by 2. Now let us substitute Tw at z equal to 0. So when we substitute it at z equal to 0, we have this 300 square into 500 minus 27 divided by 16 into 10 into 10 power 6 divided by 2 into 6.79 into 10 power 12, which is the I sub w into minus of cos h into lambda of 0 divided by cos h into 4.85 into 10 power minus 4 into 8000 by 2. When we do so, we get a very minimum value of 0.55 MPa. Now tau w at z equal to L by 2, when we substitute that, the term on the rightmost side becomes minus 1. Basically, when we do all that stuff, we get a value of 1.69 MPa. The distribution of shear stresses, as you can see here, is parabolic in nature. This is the shear stress due to warping torsion. Now let us find out the normal stresses in the flanges. From the flexure equation, we have m sub f divided by I sub f equal to E into d square u sub f divided by dz square. This equation has been solved in the previous classes. Pictorial representation is shown on the right hand side. Here u sub f equal to h by 2 into gamma. Gamma is the total rotation that takes place, and m sub f divided by I sub f equal to E into d square of gamma into h by 2 divided by dz square. The lateral moment in the flanges m sub f equal to EIF into h by 2 into d square gamma by dz square. From flexure equation, m sub f divided by I sub f equal to FBW divided by x. The normal stresses in the flange due to warping is given as FBW equal to m sub f divided by I sub f into x. So FBW is maximum at x equal to b by 2, which is at the edges of the flanges. So the FBW equal to EIF into h by 2 into d square gamma by dz square into b by 2 divided by IF. Here E into IF into h by 2 into d square gamma by dz square is the value of m sub f, and b by 2 is basically the value of x, which is the maximum at the edges of the flanges. So this can be further simplified as E into bh by 4 into d square gamma by dz square. We know that d square gamma by dz square is given as d square by dz square into T divided by 2 Gj into lambda z minus sin h into lambda z divided by cos h into lambda L by 2. So now we have d square gamma by dz square equal to T divided by 2 Gj lambda into minus lambda square into sin h lambda z divided by cos h lambda L by 2. So FBW equal to E into BH by 4 into T divided by 2 Gj into minus lambda square into sin h into lambda z divided by cos h into lambda L by 2. So here FBW is minimum at z equal to 0 and maximum at L by 2. So which is basically the normal stresses is maximum at L by 2. And so in the right hand side we have this pictorial representation of the I section that we are discussing here. So FB at z equal to 0 is given by this equation. Here this is a big equation here. We substitute the value of E as 2 into 10 power 5 and then B equal to 300 and then H equal to 500 minus 27 divided by 4 into the value of T is 10 into 10 power 6 divided by 2 into G is 76923 into J is 4.16 into 10 power 6 into lambda is 4.85 into 10 power minus 4. into bracket open minus of 4.85 into 10 power minus 4 the whole square into sin h into lambda of 0 divided by cos h into lambda is 4.85 into 10 power minus 4 and length is given as 8 meters, so 8000 mm divided by 2. This entire equation becomes 0 because sin h into lambda of 0 equal to 0. Bw at z equal to 0 is 0. Now, if Bw at z equal to L by 2, when we substitute it, we get the same equation, except that rightmost side we have sin h into 4.85 into 10 power minus 4 into 8000 divided by 2 divided by cos h into 4.85 into 10 power minus 4 into 8000 by 2. So, when we run the numbers, we get 51.59 MPa as the bending stresses or the normal stresses that acts in the flanges, right. So, the pictorial representation of the flanges are shown here. You can see at the top there is the minor axis bending for the top flange is acting in one direction. Here it is basically bending such that the right hand side of the flange is in compression and the left hand side of the flange is basically in tension. The opposite is happening at the bottom. As you can see, there is a reversal of these stress arrows that are shown here. This basically is the definition of bi moment, the bending that is happening at the top flange and the bending that is happening at the bottom flange in opposite directions represents more or less the bi moment. Now, let us look at problem 3. Here we have a 300 mm I-beam with flanges and with a web of 12.5 mm thick is subjected to a torque T equal to 4.9 kilonewton meter. Find the maximum shear stress and the angle of twist per length. The cross section dimensions are shown here. Basically, it is an H section because the depth is equal to the width of the section. So, the aspect ratio is 1. Such sections are not called as I sections, but they are called H sections. The solution here from torsion equation is T by J equal to tau by R and tau equal to TR by J. The calculation of torsional constant J, we need to find out the slenderness of the section, which is B by T sub F. 300 divided by 12.5 is 24 greater than 10. Similarly, D minus 2TF divided by T, which is 300 minus 2 into 12.5 by 12.5, which is equal to 22, again greater than by 10. We can use K1 equal to 0.333 or 1 by 3 for J equal to K1 into BT cube. So, J equal to 2 into B into T sub F the whole cube divided by 3 plus D minus 2TF into T cube by 3. So, when we run the numbers, we get J equal to 56.97 into 10 power 4 millimeter per 4. Now, we have to find out the maximum shear stress and the angle of twist per unit length. So, the maximum shear stress occurs at R equal to T. So, tau max equal to T into T divided by J. The first T represents the torque, second T represents the thickness, J is the torsional constant. When we run the numbers, we have tau max equal to 107.52 MPa. Here the thickness of the flange is equal to 12.5. Now, the angle of twist per unit length is given as theta. From the equation of torsion for circular cross sections, we have T equal to Gj theta. So, we have 4.9 into 10 power 6 equal to 76923 into 56.97 into 10 power 4 into theta. So, theta is given as 0.11 radians per meter length. So, with this one, we complete problem 3 for this session. Thank you very much.